morning, ladies and gentlemen. It is my honor to share our research on oil oxidation during oilfield air injection production process. This is the outline of my presentation. First, I will introduce the background of our research. China ranks 5th in the world in heavy oil and oil sand recoverable resources, which are mainly distributed in the Bohai Bay Basin and the Zhongguo Basin. Liaohe and Xinjiang oil fields have the largest heavy oil reserve. For many brown oil fields with heavy oil in China, the oil production rate and oil steam ratio are both quite low. Evaluation for suitable EOR methods for these oil fields is quite important, and in-situ combustion is considered as a good candidate. In-situ combustion is also called fair flooding. For this production method, an electric heater or an igniter will be inserted into the reservoir and heat the reservoir to 500 degrees Celsius. And then we injected air. Normally, 10% of the heavy oil will be burned as fuel, and 90% of oil will be produced for one-dimensional combustion tube test. For field operation, nearly more than 60% of oil will be produced for by in-situ combustion method. So, PetroChina began the in-situ combustion pilot in the year 2009 in Hongqian Block, Xinjiang oil field. Before in-situ combustion, this block is developed by steam injection, which is a system silic steam stimulation and steam flooding. For the steam injection method, the recovery factor is 29.5%. Then the reservoir is depleted and shut down for 10 years. In the year 2009, the in-situ combustion pilot began. And after 10 years, by the end of 2019, the accumulated oil production of in-situ combustion is 155,000 tons. And the state recovery degree of in-situ combustion is 36%. The average monthly production of in-situ combustion is 1,200 tons, and the accumulated air-oil ratio is 2,900 cubic meters per cubic meters. So the pilot test is very successful. The vertical wire fair flooding pilot in Hongqian Block shows very promising results. So the in-situ combustion is used as strategic EOR method for brown oil fields with heavy oil in China. For in-situ combustion process, the oxidation of crude oil in the reservoir is quite complex. Normally, for heavy oil and different oil, we think that for heavy oil, most reduction heat is released by the HTO high temperature oxidation process, and the low temperature oxidation process releases very little heat. But for the light oil, the reaction heat is mainly released by the low temperature oxidation process, and the high temperature oxidation process releases very little heat. For heavy oil in-situ combustion, in the reservoir, it can be divided into many regions. For example, combustion zone, combustion front, and coking zone, steam zone, oil bank, and the residue oil area. In these regions, the most important one is the combustion front. The reaction here is high temperature oxidation. It releases most of the heat for this process and provides energy for the in-situ combustion. But for the study of in-situ combustion with different oils, different researchers published data with different apparatus. The results are quite different. Because the activation energy of high temperature oxidation influences the reaction temperature, so the combustion front temperature may vary with each other, may have a big difference. So the application of in-situ combustion on heavy oil reservoir could be limited by the oxidation kinetics of oils. Another problem is for high pressure in-situ combustion test, we found that the tubing and casing were damaged by the high reaction heat during electrical ignition process. This pilot test is carried out in the Tuha oil field, and the reservoir pressure is 22 megapascal. Influence of pressure on reaction rate and reaction heat need to be studied. Now I will introduce our research about HTO kinetics of different oils. We use TGA to study this process. TGA can record the sample weight during the heating process of the oil sample or the coke sample. First, we studied the influence of sample preparation methods. For the oxidation with pure oil sample, there are multiple reaction peaks in HTO regions. That is because for this oxidation process, the oxidation only takes place on the surface of the oil. The bottom oil can't reach the oxygen, so the reaction is not even. So we mix oil with silicon oxide, so oxygen can pass through the porous space between silicon oxide particles. All coke will be deposited on the silicon oxide surface, so they can react evenly during the experiment. So this result can be used to calculate the intrinsic oxidation kinetic parameters. We also studied the calculation method influence. These two figures show the results of two single curve kinetics determination methods. We can see for the same oil, if we use two different single curve kinetic calculation method, the activation energy result is quite different. The reason is that for this method, we use only single reaction curve to calculate three different parameters: activation energy, pre-expositional factor, and reaction order. This can cause a very big errors. So we use Iso-conversional calculation method to avoid the influence of fuel mechanism functions, which means we didn't calculate the reaction order or other forms of mechanism function of the fuel. In these conditions, we use different heating rates test result and get the experiment data with the same conversion rate. So at this condition, we can calculate the activation energy and the pre-expositional factor A very exactly. We choose some oils from PetroChina, air injection, field pilot. In these oils, there are some light oils with the viscosity about 20 to 45 at 50 degrees Celsius. And we have some heavy oils. The viscosity is about 2,000 to 40,000 centipoise at 50 degrees Celsius. For these different oils, the oil property and the viscosity are quite different, but we can see at the same reaction conditions, different oil have similar reaction temperature region. For LTO reaction, the temperature region is about 200 degrees Celsius to 400 degrees Celsius. And for high temperature reaction, different oil show the same temperature region is larger than 400 degrees Celsius. In order to calculate and compare the activation energies of different oil from both light oil and to heavy oil, we use two other different Iso-conversional methods to calculate. We can see with these three Iso-conversional methods, different oil, although the viscosity are quite different, but they have the very similar high temperature oxidation activation energy. The activation energy is about 130 to 150 kilojoule per mole. We also calculate the high temperature oxidation kinetics parameters for other carbonaceous material fuel. For example, the soot captured from diesel engine and the commercial pure carbon with carbon content 99.5%. So for these carbonaceous fuel, the high temperature oxidation activation energy is also in the same range, 150 kilojoule to about 170 kilojoule per mole. So we can see for high temperature oxidation with different property oils and other carbonaceous fuel, the activation energy are in the very small range from 130 to 170 kilojoule per mole. So for different oil with different viscosities, we can have the same high temperature reaction temperature region. In order to explain this, we carry out the kinetic cell experiment. For kinetic cell experiment, we fill the reactor with the oil sand in the middle, and then heated the kinetic cell temperature linearly to 600 degrees Celsius. And we measure the outlet oxygen, carbon dioxide, and carbon monoxide. So for these two figures, with different two oils, kinetic cell oxidation results, we can see for the red line, it represents the oxygen difference of inlet and outlet. And the blue line represents the oxygen in the produced carbon dioxide and produced carbon monoxide. So when reaction temperature is larger than 400 degrees Celsius into the high temperature oxidation region, we can see the depleted oxygen are the same of the oxygen in the carbon dioxide and carbon monoxide, which means for these oxidations, the fuel is mainly the carbonaceous coke, and the content of hydrogen is very small. The third part is our research about crude oil oxidation heat effects. In this part, we use three apparatus, Mittler, TGA, and DISC apparatus, TGT accelerating rate calorimeter, and the TA company Q20P pressure DISC apparatus. First, we studied the DISC curve at an atmospheric pressure to study the oxidation heat effect of different oil with different viscosity. So for these 6 samples, 2 are light oil samples and 4 are heavy oil samples. We can see different from previous research, heavy oil also have very prominent LTO reaction heat effect. And for light oil, the HTO reaction heat content is also very large, but it is nearly half of that of heavy oil. The reaction temperature region, for LTO reaction temperature region, light oil and heavy oil have nearly the same temperature region, and for HTO also nearly the same temperature region. If we compare the heat of LTO and the heat of HTO, it is at nearly the same amount. But for the LTO oil sample will react and release heat. But for HTO, only 20% of oil will be converted into coke. And this coke will release the reaction heat of HTO. So if we consider the specific heat of fuel, HTO is much higher than LTO. So for field operation, if possible, we should operate the in-situ combustion at HTO mode because it is much more thermo efficient. For the DST test, we can see that heavy oil can produce the reaction heat at low temperature oxidation region, about between the 200 degrees Celsius to 400 degrees Celsius. But below the 200 degrees Celsius, DST cannot measure the reaction heat. So we use the accelerating rate calorimeter to study this process. We measured the ARC test results with 5 different oils. The red one, blue one, and the purple one. The first 3 ones are the light oil result, and the last 2 ones are the heavy oil results. So we can see in the temperature region from 160 to 240s, the heavy oil also have a very prominent reaction heat effect, which is not smaller compared with that of light oil. So for heavy oil, it can have a very different heat release region compared with the HTO. Then we studied the influence of pressure and oxygen pressure on the oxidation heat effects. When we increase for the Liaohe and Tuha heavy oil, when we increase the pressure of reaction, we can see the temperature of both LTO and HTO both decrease. But for HTO, the heat itself didn't, the pressure didn't increase the HTO reaction heat amount. But for LTO, increasing pressure will increase the LTO reaction heat. That's because for HTO, the fuel is oil. So when pressure is increased, more oil will be contained in the sample holder and react with oxygen and release the heat. These results are the 2 different light oil, the influence of pressure. We can see when we increasing the pressure, the LTO heat also increase a lot. And when reaction pressure is high, we can see a very sharp reaction heat peaks. For the influence of oxygen fraction, we carried out these 2 tests at the same pressure, but with different oxygen fraction. We can see when we increase the oxygen fraction, the reaction temperature also decrease for both heavy oil and light oil. But for the reaction heat, oxygen fraction didn't influence the HTO reaction heat, but increase the LTO reaction heat. For these 2 tests, we compare the results with the same partial pressure, 2 different tests. For these 2 tests, the pressure is different and oxygen fraction is different, but the partial pressure of oxygen is the same. And we can see these tests are nearly the same. So which means for the reaction of both LTO and HTO, the reaction rate is proportional to the oxygen partial pressure. These test results also confirm this conclusion. So in final, a conclusion. TGA apparatus and Iso-conversional methods were used to study the HTO kinetics of different oils. The activation energy range for 3 oils were 130 to 154 kilojoule per mole. Kinetic cell and effluent gas analysis technique were used. Fuel composition were calculated by the effluent carbon dioxide, monoxide, and oxygen concentration. The results show that the fuel of HTO reaction were coke with very low hydrogen content. Although the viscosity and compositions of oil were different, the fuels were similar. So TGA analysis showed similar HTO kinetics for different oils. Oxidation test showed that oil samples with different viscosities have similar LTO reaction temperature region and HTO reaction temperature region. Heavy oil samples also have high LTO heat effect. The measured reaction heat of HTO by unit mass of coke is larger than that of LTO. Oxygen partial pressure has strong influence on light oil LTO reaction heat. When pressure or oxygen fraction increase, LTO heat of light oil sample increase. Thank you. That's all for my presentation. I'm glad to answer your questions.